Imagine you were playing a new video game. You were at the character creation screen, tweaking fur colors, picking out a color, and giving your new friend a name. For the developer, writing the instructions for this one dog is simple, but what happens if the game becomes a hit and 100,000 players all want their own unique dogs running around the same world at the same time? To manage that scale, programmers use a system called object-oriented programming. It is a way of organizing code so that it mimics how things work in the real world. This approach stops developers from having to rewrite the same basic instructions over and over, making it possible to build massive, living digital worlds. A developer first creates a class, a master blueprint describing a dog. When the game uses this to create your character, that living dog is the object. It has personal facts like color, representing its state, and actions like barking, known as its behaviors. So the class is the abstract idea on the drawing board, while the object is the specific interactive character the player actually controls in the game. To see how this works in practice, let's look at how we translate our dog blueprint into actual Python code. The class dog command opens a blueprint container. Species equals canine is a class attribute shared by every dog. Next, the init function acts like an automated assembly line, where self tracks each individual pet, holding its unique data like name and age. This small block of code acts like a universal machine, capable of generating a nearly infinite number of unique digital pets. Now, let's watch what happens when a player finally hits create and gives their dog a name. Code like dog1 equals dog, buddy, 3 is the moment of creation, plugging specific values into the blueprint to bring a dog to life. Later, the game uses a simple dot. Typing dog1.name tells the engine to pull out the exact name we assigned. This dot is a direct wire to the object's brain, allowing the game to check its health, name, or species at any time. As the game expands, players will want more variety: cats, birds, and even tiny puppies. To add these quickly, developers use a few special rules of organization. First is inheritance. Instead of writing a new puppy blueprint from scratch, it simply inherits all existing rules from the dog blueprint. Then, polymorphism allows the game to send one command, like speak, and get different results. The dog barks while the cat meows. These rules allow a developer to add hundreds of new creatures and features without having to repeat the most basic work. To keep the game running smoothly, the computer also needs to protect each pet's data from accidental errors or glitches. Encapsulation bundles a pet's data in a protective shell, preventing other code from accidentally changing its age or name. Finally, data abstraction simplifies things. As a player, you only need to know the jump button works without seeing the complex internal math. When these four concepts work together, they allow a developer to manage thousands of moving parts while keeping the code clean and easy to update. Understanding these blueprints helps us see the logic behind the digital worlds we play in every day, reminding us that every complex character on screen began as a simple, organized idea.